Okay, let us start. Oh yeah, still in college ah. Okay, main thing to when you do your revision, I think you should be starting doing your past year paper already lah by now. Year by year, right?
Yeah, started.
Your syllabus should be around with you lah. Then you know what to cover, what is not in the syllabus. Okay, let's start with 8.1. Right, standing wave or stationary wave. When two waves, right, they must be all the same type, same speed, same wavelength or frequency lah. Traveling in opposite direction, that's important. Traveling in opposite direction, that's a condition. And they cross a region, a new waveform is obtained. Right, so that is the standing wave. The waveform is stationary, so it's called standing wave or stationary wave. The particles in the medium where the standing waves are formed vibrates either in phase, like here. If you look at this standing wave, right, we just draw the different position of the wave as the time goes on. So these are the standing wave. So all these within these knots will be vibrating in phase, or it will remain stationary like this point. Permanently stationary, that is the knot, or 100 degrees out of phase. Right? This one, a point here, a point within here, and a point within here will be 100 degrees out of phase. Okay, same within here and within here, 100 degrees out of phase. Okay, so this one you need to remember principle of superposition. When the waves meet at the same place at the same time, the resultant displacement equal to sum of the individual displacement. Okay, that's what it means. When they meet, they add up. Okay, so normally in exam they can ask you lah, like this type. Of course, not so simple like that. Draw for you lah. They have two waveform, and then they will ask you to add up lah. They won't ask you to draw the whole waveform, but ask you to find the resultant of the waveform lah at one particular time or position. So in this case, you must remember displacement one is positive up, down is negative. So you subtract. In this case, you get 4 meter upwards. Okay, remember displacement is a vector. Or like this case, both are in the same direction, you just add them up. Right, so you get 10 meter. Sorry, 10 plus 6 is 16 meter upwards. Then intensity, you need to remember the formula. K intensity is proportional amplitude square. If the amplitude is A, sorry, the intensity will be I equals to Ka square. If the amplitude is double, then you just, this amplitude there, you replace it with 2A. So you have 4I, right? Got 4A square, your Ka square is your I, so you got 4I. Okay, but if you can work mentally, it's easier. Two times is just square that is 4I. Okay, so you won't bother about that anymore. Standing wave and interference. In standing wave and interference, that the wave of the it must be of the same type, same kind. That means sound wave and sound wave, light wave and sound wave, light wave, same frequency or wavelength, same speed. Another condition would be polarization. Right? It must be the same polarization. That means if it's polarized upwards, the other one must also be polarized upwards. Okay, the two terms that are interested will be constructive and destructive interference. Constructive interference or reinforcement. Right? Remember, these two waves are on top of each other. So we cross of the two waves coincide. The two waves are in phase. The amplitude add up. So if each of this is A, then it will be 2A. So intensity will be 4I. Or if each amplitude is A and B, then you just add A plus B. So if you slide, you see greater intensity. If sound, you hear louder sound. Okay, in this case there, one moving to the left. So the two wave add up together, the resultant wave is the resultant waveform. Okay, I think we have done this one already, so we won't bother to go slowly with you. Do the same thing, just repeating. Okay, so destructive interference, or we call it cancellation. When the two sets of wave cross, the crust meet the trough, or we say 180 degrees out of phase, we have complete cancellation. Both of them have the same amplitude. So if we slide, you see a dark line or dark band. Sound, you will hear no sound. Okay, example, one wave traveling to the left, one wave to the right. Right, and you will get a resultant 0. Right, or in this case, just a repeat of that, 0. Are you okay with me now so far? Okay.
May I know transverse waves, right? Why is it that only transverse waves can be polarized?
Why is it longitudinal wave can be polarized? Is that what you're asking?
Yeah, like why longitudinal cannot be?
Oh, remember that if you look at me, transverse wave go this way, up and down. Or maybe I show you the diagram easier.
Okay.
Okay, this is transverse wave. Longitudinal wave, the particles are moving parallel, vibrating parallel to the direction of motion. So that's why you cannot polarize it. Okay, look at the picture, this picture there. This is the direction of travel. The direction of vibration is also the same direction of travel. So if you are polarizer will just allow it pass through, doesn't stop it. Whereas for this particular one, it's unpolarized. So the polarizer will allow only the part that is parallel to the slot to pass through. Can? Okay.
Okay.
important that if you want to see complete cancellation, then both of them must be of the same amplitude. Right? If it's light, you see dark line. If it's sound, you hear no sound. Right? Like you see, these are your disruptive interference. You see that this is your Young's double slit. Right? So it's just for your information where we use in communication where the two waveform are. This is your, because this is a signal. This is your carrier. So we add the two to get this resultant. Okay, it's normal in your syllabus. It's removed already. Okay, so the conditions, remember to need to memorize it. And the common thing they will ask you is what does the speed mean? Right? The speed is the speed of the incident progressive wave and the reflected progressive wave. That's all. That's a natural phenomenon we see where standing wave is formed. Okay, I think we won't go into all the great detail. Let's go to okay, this is called the mode of vibration, the second mode. And if you look at the second mode, you see that this usually we draw two sides, one side and two sides, and that's the other side. So normal question would be asking you would be, if we start from here, this part at t equals 0, then quarter is basically going from top to the equilibrium position, a quarter t, and then go to the lower position, half t, then go back to the equilibrium position, and 3/4 t, and then come back, will be t. Okay, so you should be able to draw that. So if it's if we start from here 0 at time 0, then this one will be a quarter t. The dark one will be half t. Right? Depend on where you start. And this is called the node where it is completely 0 all the time. Antinode is the between the two nodes. Right? Midpoint there, A. And then when you want to look at the wavelength, we look at one side only. Don't consider two sides. Just consider one side. The dark one, and that's the wavelength. That's half the wavelength. From north to north is half a wavelength. From north to anti-north is a quarter wavelength. Stop me if you want to ask question.
Sorry?
If you want to ask question, stop me.
Okay.
Okay, you can use your hand to produce standing wave, right? But usually we don't do that. Right? This one is the lowest frequency, one loop. And higher frequency, two loops. So usually we will use a signal generator or vibrator. And that is your string passing over the pulley and attached to a hanger. The hanger is basically with the mesh added here to provide the tension on the string. Okay, the speed of the wave on the string is determined by the tension. The tension is determined by this mesh. And the mesh per unit length of the string. Right? That part you don't need to know too much. Right? So vibrator is to cause it to oscillate up and down, just like a hand. Right? Cause it to go up and down. And then you will cause the wave to move down and then this is your fixed end. The reflector wave will, and the incident wave will interfere here. So the lowest frequency, you can change the frequency of the vibrator. That's the reason why you connect it to the signal generator. So this part at the two end there will be the node, and then the middle part will be the antinode. This is for your information. It doesn't mean that exam cannot come out. I think it had come out 1 year before, asking you, telling you that this is the speed of the wave, this is the tension in the string, determine the unit for this one, this symbol, that's all. It has come out before. So it doesn't mean that the formula cannot come out, it can come out, but you should know how to determine the unit for mu. So if you know that, then you know that your answer must be mass per unit length. Okay, so that's the different mode of vibration, displacement distance graph. Right, that's for first frequency F1. This for 2F1, 2 loops, 3 loops, so the 3F1. Okay, let's concentrate at the first one, called the fundamental mode. Right, don't let that distract you. Just look at the 2 loop. This one loop, that's all. As the frequency of the oscillator is increased at a particular frequency called the fundamental mode, we will see stationary waveform. We see one loop lah, right? Less than F1, we won't see any loop at all. And then the first overtone, if we increase the frequency, there's a first overtone, 2F1, and so on. Right? We got 3F1, 4F1. You need to know how to draw also lah. Right? The one thing to remember is the wave profile appears stationary. It doesn't move, right? Appears stationary. It's just like skipping rope, right? Going up and down like that. Right? For the first one, where these two are this at the end there are the node. They just go up like that. Right? The crust and the trough do not progress. Right? There's a crust, there's a trough, there's a progress. It just go up and down only. Right? There's a trough, go up, there's a crust, goes down. And the energy stays in the same place, it doesn't move. Between successive nodes, there's a node here. The particles vibrating in phase, but different amplitude. Okay. All the particles here, all the particles within here vibrate in phase. That means this is the fundamental mode. They just go up and down like that, that's all. Right? The largest amplitude will be the antinode there. Others, they have amplitude, but smaller amplitude. To the left and right of an antinode, the particles are 180 degrees out of phase. Sorry. I think there's a mistake here. Okay, to the left and right of the node, there's a node. This part is a node. Right? To the left and to the right, they are 180 degrees out of phase. This part is moving up, this part is moving down. Or this part is moving down, this part is moving up. Right? That's why it's 180 degrees out of phase. I seem to have a problem all the time with the video. Okay, so that's the actual experiment setup. During my time, we don't have all this sophistication, so we use paper rider. Paper rider just pieces of small, tiny paper we make into a V shape, and then we just put evenly space it lah. So you're supposed to know that at the node there, antinode there, it will be thrown off lah. At the node there, it will remain stationary. Okay, let's look at the physics involved. Look at the fundamental mode. Okay, these are your fixed end. Okay, these are your fixed end. So if you want, let's just review that, what is happening. These 2 points. This point and this point are the fixed end. So you should be able to write where is the node, where's the antinode, and where's the node. Fundamental mode, one loop, or we call it fundamental frequency or first harmonic. Right, so you should be able to read that this is half a wavelength equals to L. So we call this the first wavelength, lambda 1 equals to 2L. And the frequency is V over lambda 1, so V over 2L. So that is the fundamental frequency. Right? Sometimes people will use a Greek alphabet like nu, or we use English alphabet frequency F, same thing. And second mode, right? 2 loops, same length. You'll be able to say, okay, all these are the antinode, all these are the node. So we call it the first overtone or second harmonic. So there is one wavelength for one node, the other node there, one wavelength L. Right, so in terms of the previously, it will be half lambda 1. So it's F2 is V lambda 2 or V over L. So it's V over 2 F1. Okay, so you should be able to derive that all that for the second overtone or third harmonic. That's your lambda 3. And as I said, this is for your info. The speed is determined by the tension of the string and the mass per unit length of the string. Okay, so in general, you need to be able to memorize the fundamental frequency. And then for any number of loops, n, fn, the frequency will be n f1. N is just 1, 2, 3, 4, and so on. Sorry. You need to also remember this one will come out usually in the objective question. Lambda n, right, for n loops. Here you just multiply lah, n times f1. Here you just divide. Lambda 1 divided by n. Lambda 1 is 2L. Okay, or we just summarize it. Combine all them together. Summarize it. Any question to ask so far? Okay, if not, let's carry on. Second harmonic or first overtone, let's just look at that. Make sure you know where to identify where's the N. N is for node, A is for antinode. All points between successive nodes are oscillating in phase. This is one node, this successive node. All the points here, or all the particles here are vibrating in phase. Point to the left of a node is 180 degrees out of phase with on the right. Right? If you take this as your node, point to the left and point to the right are vibrating 180 degrees out of phase. What's the phase difference between successive nodes? What's the answer? Successive notes, they're vibrating in phase. What's the phase difference between points to the left and right? To the left and right.
180 degrees.
Good. 180 degrees out of phase. Okay, let me just test you a few things before we start to go further. We won't bother about that. You can. Okay. If each division has an amplitude of A, right? Division outwards there have amplitude of A, and the intensity is I. Determine the resultant. You should be able to draw the resultant. Right? This type of simple thing that can ask you to draw lah. What's the resultant amplitude? Yep. What's the resultant amplitude?
6A.
Okay. This one is 2A. This one is 3A. Sorry, 4A. 4A plus 2A, 6A. Good. What is the intensity? Yep. What's the intensity?
36I, I think.
Just square that off. Square the 6. You get 36I. Okay, that's the working. Okay. Have a go at this one. What is the answer? A wire is stretched over 2 points, Q and R, a distance 4x apart. 3 light pieces of paper rest on the wire as shown. These are the light paper or paper rider. When the wire is made to vibrate at a particular frequency, the middle piece of paper stays on. This one stays on. The other fall off. These two fall off. What's the wavelength of vibration produced in the wire? Yep. What is your answer? Speak a bit louder, can't hear.
4x. 4.
Okay. See, good. Just draw off. Just draw. That's your stationary wave. Okay, what's the wavelength of the wave? This is one of the past year paper.
One point.
1.5 meter, okay. Or 150 cm. Frequency? Calculate the speed. The frequency is given you now. Calculate the speed of this on the string.
540 meters per second.
Okay, they just want you to know the formula. Write down the formula. Always remember, write down the formula. That's how you show you're working. Sometimes the formula is worth 1 mark. Okay, in 10 minutes time, you have to stop for a while. Because this one will start automatically in 10 minutes time anyway. Okay, by reference to the formation of standing wave on the string, explain what is meant by the speed calculated. Yep.
So it's about the wave traveling from one end to the other and then back per unit time. Right?
They're asking you what does the speed mean? The speed that I calculated, what does it mean?
So it's like the distance that the wave travels from one end to the other end and then back?
No need to go to that great detail lah. It's just the speed of the incident and reflected wave. That's not good enough. Right? This is the speed of two waves traveling in opposite direction. Okay.
Okay.
But since they require to 3 mark, if it's 3 mark, then you have to make sure you have 3 points. This is the speed of two waves traveling in opposite direction on the string. One the incident wave and one the reflected wave. So always look at the mark lah. If 3 mark, make sure you got 3 strong point lah. Okay. Standing wave in pipe. Okay, you can either blow it. Okay, treat this as a pipe. The air there will be vibrating if you blow it, or you can hit the side there. Okay, the pipes or tubes can be classified as open or closed. Right? Open on both ends. Closed, one end is closed. Always remember whether open pipe or closed pipe. Open end you can vibrate freely. So node is often at closed end, where destructive interference occur. Antinode is obtained at the open end, where constructive interference occur. Let's look at open pipe. Remember your waveform. From crust to crust is one wavelength. From a maximum, from a crust to a trough is half a wavelength. Right? From 0 to the crust is a quarter wavelength. Right? Or from 0 to another 0 is also the same half a wavelength. Okay, fundamental mode. This is a fundamental mode. Open end antinode, open end antinode. Center there must be your node. So how to draw that? Right? If you have a problem, just draw your waveform. And then start with maximum and minimum. That's the simplest one you can draw. That's the one that I've drawn here. And then block out the others, so erase it off. And identify your antinode at the open end, and then your node at the midpoint. And then able to identify this is your half wavelength for this lambda one. That be L or cross multiply. Lambda one is 2L. F1 is B over lambda 1 is B over 2L. Okay, second one, the same thing. Maximum to the minimum to the trough is what is the first one. The second one will be here. Right? We call it first overtone or second harmonic. Just erase the other part off. That's what we get. Okay, so the wavelength, that is your lambda 1 just now that we obtained these two formula. So we call this a different wavelength. So we call lambda 2 equals to L. So in terms of lambda 1, L is half lambda 1. And F2 is V over lambda 2. Lambda 2 is L. Okay, so this is 2F1. Okay, so far? You should be able to derive it.
Yeah,
Okay.
I'm still drawing.
Anything not clear?
I'm still drawing.
Say a bit louder.
I'm still drawing the diagram.
You don't know how to draw the diagram.
No, I'm still drawing it.
Oh, yeah, drawing. Okay, okay, sorry. I didn't realize you're copying. Let me know when you have completed.
Okay. Completed.
Okay, let's get
I,
it. Okay or not?
yes.
Okay, so you should be able to summarize it. Drawing on one page. There's your there's your different formula. So you should be able to summarize it. If this is F1, this is 2F1, then you will have N Fn will go N F1. Right, this is the first one, second one, third one will be 3F1. Right, same as a string. Same as a string. Right, lambda n equals to lambda 1 over n. Okay, I think we will stop here since our time is almost up. We will see. I give you 5 minutes break.
Okay. Thank you.
Okay, you can go stop here.
Okay. Thank you.